All right, folks, welcome to this Earthscope class. I think that's the official title, if I got it right. Using MsPASS for data processing on HPC and cloud systems. What a big, long title. Um, and so, uh, first, what we're going to do to start here is just some introductions and just sort of overview stuff. And then we're going to dig into material. So I'll start. The first introduction is me. I'm Gary Pavlis. See, I have a 50-year history in computational seismology. I remember writing my first Fortran program in a one-credit Fortran course in 1973. So that's more than 50 years with cards. Anyway, long story there. But anyway, I was a professor for 35 years at IU, Indiana University, and I retired about 7 years ago, whatever that is. I'm one of the Ian Wong and I, who's the next person going to introduce himself, were the co-developers of MsPASS, along with a whole bunch of students who've helped us. So Ian, you're next.
Oh,
Just
why
say
did
a
you
quick,
make
say
your
30
turn?
seconds, say 30 seconds for about a little bit
Okay.
about yourself.
My name is Ian. As Gary mentioned, right? I used to work with Gary as a PhD student, but since graduated, we started this MsPASS project. I've been working on that for the past 6 years, 6 more years, more than 6 years actually. My background by training is a seismologist, but I been doing a lot of HPC related work since graduated. Um, so Previously I've worked at the Texas Advanced Computing Center, which will be the system that's actually which is actually the organization that's gonna provide the HPC system resource that we will be running on Wednesday, actually. Um, right now I actually just left tech a week ago because various reasons. But Gary and I had a plan to continue maintaining MsPASS and keep the project moving forward, and we still have continuous funding supporting it. So, and Gary, you had a mistake there. I'm not at AMD, I'm at ARM.
ARM, got the wrong word. Sorry.
All right. So,
Wrong
yeah.
acronym. Sorry. All right.
But yeah, that's about me. Thank you.
Sarah.
Hello, everyone. My name is Sarah Wilson. I am a cloud developer advocate at Earthscope. I work with Earthscope to build tools that will help researchers like you transition into the cloud. I'm also an administrator and a maintainer of the GeoLab environment. So if you run into tech support issues this week, please reach out to me. Slack is going to be the preferred method on the tech support channel, but you can also ping me directly or reach out via email. I've shared a little bit about my education and background here. I've worked in biomechanics, robotics, and IT support in the past. And I'm sharing that not because it's particularly important or relevant for you to know what I do, but more as a demonstration that there are a lot of careers available in science and science support. And I think a lot of times, in an academic path, you see your instructors like Gary and Ian working in a more direct and narrow focus. And I just want to share that there are lots of ways that you can be in science and science support um, and doing seismology. So thank you for being here.
Thank you, Sarah. Um, Also, thanks to Jillian, who's here, and Robert Weekly. I don't know if he's not here. He's not here today, but maybe he'll be later. And others at Earthscope. A lot of people took a lot of people to make this thing work together. And I thank you all for that, and we all should thank them for that. Um, so uh, we're going to be working today on this GeoLab, which I assume you've now all touched. And one of the things I wanted to say with this slide up is that you can multitask. I advise you to multitask, and while we're blabbing and you tune on something here, you don't want to get yawn or whatever. Make sure you're connected to GeoLab because we're going to work there shortly, and you'll be behind if you don't connect now. So I assume you know how to do that by now, and so that'll help if you do that because there's a little startup delay if you may have kind of recognized when you started. So, but this is a great facility. It is a cloud gateway, which we'll talk about at length on Friday. So Sarah will be one of our resources there. So I want to go over a little bit of course business first before we start give any kind of lecture material about anything technical. Oh, and yes, there's the first one. Tammy is going to tell you a little bit about this course credentialing thing, which will hopefully motivate you a little bit about doing some of the work for this class. So go ahead, Tammy.
So hi, I too am a PhD student of Gary's. So I am now years ago. So now I am a seismologist and instructional designer with EarthScope. And so I'm excited recently, EarthScope has added a micro credential for our technical short courses. So specifically for MsPASS, the credential that we're offering is at a proficiency level, which means the instructors are validating your skill acquisition with structured grading. So that's a higher level credential for us. So we reviewed the material in the course. On the right side of the slide is actually the website that's linked to your credential. And so you can see we've broken out the technical skills that this course is designed to train. So once you've received this credential and share it, link to the image wherever you share it is a description of your experience and the skills that you've successfully demonstrated. So my ask to you is please attend the 3 days this week. There are a few short exercises in the Moodle environment for each day. And if you complete 80% of the course material with 70% or better, we will issue this credential for you. So do you have the second slide as well?
I do. I'm trying to, there's, yep.
So we're working with Credly. So after the course ends, you'll get an email from Credly. All you need to do is click on the link in the email. The badge, wherever you share it, remains linked back to that detailed page, so that accomplishment follows you. If you have any technical questions or problems during the course, the Slack is the place to go. But by the time the course ends and you receive this credential, if you have any trouble with it, you can email us at that email as well. So thanks, Gary.
All right. Thank you, Tammy. Okay. So I got as an old guy, I thought I'd first of all give you some advice I can't resist doing is being years as an academic advisor. A few useful things I call axioms of the modern world. This is one I've really thought is really appropriate, especially for a lot of things, but especially for IT issues. That everyone's an expert and everyone's an idiot. And I'll talk more about that in a minute, but one of the critical things is something you may have never heard of called the Dunning-Kruger effect, which is I thought this is a really interesting thing about the modern world. You might want to watch that video at some point for fun. It's like 20 minutes long, so it gets a little long, but it says why stupid people think they're smart. The Dunning-Kruger effect is comes from a psychology paper which shows why people think they know more than they do. And that's why I say everybody's an expert and everybody's an idiot. Now, so as a group of people in science, it's a very important skill to not fall into the Dunning-Kruger effect because science is all about distinguishing what is true and what you kind of know what you know and what you don't know. And so anyway, it's a useful thing to know about because it's the psychological thing to recognize your own weaknesses and to fight it all the time. The other little general point I'll make to you is a career advice is in this modern world, the way things are going, you really got to shape what you do, your career, for something that won't be done by a robot because it's clear that things are changing. That's one of the most profound things that are changing over in the near term. So here's some just words about this, about everybody's an expert and everybody's an idiot. And that is, I'm not going to read all that, but really what it is that you can go back and look at this PDF later and you can dismiss or whatever by preaching, but it really isn't. I guess the really key point is two things about being an expert is you have to always know the difference, what you do and don't know. And it also points to the importance of being a lifelong learner because you would never keep up. You just have to constantly change what your expertise is. And so taking the reason I'm pointing this out is taking classes like this is important. So do it and to do it right and learn from it. Okay. And the other one's just, okay, that's enough. For a few more things like that is just sort of extending what I talked about before. I won't dwell on this too much, but this is really the important thing about as you develop your career to develop, it's because of the world changing with information the way it is right now and the way things have changed. So I think that for you to be successful, you really need to work on things like problem solving skills and not the grunge work that a lot of people have spent their careers doing. You have to you have to be creative, and as the world is going to more and more reward creativity and ability to assemble data and not just spit it out. Because it used to be the kind of there were people who had professors, for example, who their whole career was spent on minutia that are totally ridiculous now because Google can do it better than they can. And so anyway, developing that kind of thing, programming skills like in this class are important. So now, course corollaries is that don't be afraid to ask questions because and you're also going to have two things at the same time. You're going to be, since everybody's an expert and everybody's an idiot, there's going to be things you know really well. It's like, oh, I don't need to know this. I already know that. And then there's going to be things that you say, I have no idea what this guy's saying, right? And so you need to recognize. I want you to be ready to ask questions because I can't answer them if I don't know you don't have them, and the odds are high that somebody else won't either because there's so much complexity in the modern IT world that you cannot possibly know it all. And it's all about what you assemble from what you can glean from the internet these days about how you do stuff. But anyway, my mechanisms here is incorrect. I was told that what other the chat, what you're going to use is if you have a question, put it into Q&A, not Zoom chat. And Tammy and Jillian are going to monitor that. In case if I get too many questions come up, then they're going to stop me, and you can they'll answer your question, or we'll save them for a while to the end. So if I guess we don't have, I don't think we have a raise your hand method or whatever. We'll just use the Q&A and then we'll come back to those things during things. I have a couple discussion things and then we'll just talk for a little bit. But if you have other questions, don't come to my office hours. I'm doing that trying that out. I think that'll help you with individual things that will help if you run into barriers as you do these exercises. Hopefully that'll help you learn this better. Okay, so some assumptions about where I am. That you've actually done this pre-course material. So that way, I can know that you could get into GeoLab right now and you know how to run a Jupyter notebook. So I'm not going to spend any time on that kind of stuff. And I'm also going to kind of assume you did that pre-course material. So you may not be intimately familiar with the course I gave those three lectures and that material, but at least you kind of had been exposed to it. So I'm not going to revisit that material, except maybe where I thought it was important. You really know that material. So anyway, so you do need to get this certification. You do have to do the homework on Moodle that's assigned. And it took a lot. I have to say this is an addition to this class. This is the first time we've done it this way because of this new course management system that EarthScope started. But I think for a virtual class, it is absolutely essential. I really like the ability, what it can do for you, because it's too easy when you're sitting here listening to somebody blab like me to just kind of tune me out. Blah, all right, what the hell is he saying? I don't. But these quizzes like this can reinforce the material and really cement it in your head. Otherwise, you tend to you get overwhelmed with this stuff. And I tried to make the quizzes as best I could, the quizzes and assignments to reinforce the material we're going to cover. So that's the idea, that you really should, if you're going to get something out of this course, you really do need to do those assignments, because then that will reinforce what you do. And you've seen already the way it works is that if you get the wrong answer, it'll tell you well, you made you think about this, you need to. So all the questions are designed that way. So think of the quizzes and the material you do as the homework assignments as a learning exercise, not as grunge work you got to do, because it really is essential, I think, to learn this material. Okay, so this is the 3 sessions we're going to have. Today is kind of an overview of everything. some major things you need to know that I've kind of selected that I think that we need to know, that you need to know. Uh, then on Wednesday, Ian already mentioned this, we're going to be doing work on a high performance computing cluster at TAC called Frontera. And we'll also do some stuff on GLab. So it's going to be both that day. So we're going to be, anyway, we'll get to that later. And the last session is completely new to this class. This is the first time we've ever tried to do this. Is to work with what's available right now as the cloud interface, which you're on GeoLab, but some other capabilities about how you're going to be able to access and work with the Earthscope archive, seismic archives in the now and in the near future. And that's what Sarah will be presenting a thing on Friday about where Earthscope is going and what the sort of timeline is and what you should be expect to be able to do soon. So, okay, so this is my last slide. I think about business like this. That's getting I talk too long, but so everything will start like this with a short overview lecture, and then everything we centers around these notebooks. But the notebooks are also kind of self-contained. I think maybe that's my next slide, actually. I'm actually kind of repeating things here, which I just said. So I think, yeah, this is the notebooks. You should note are actually are completely self-contained. They contain material that's written about what's done to explain what the steps are done. So the notebooks are meant to be instructional, but they're also a good example of reproducibility of science. So the real workflow you ran before we started here, I had you do before the class started, is a type example that after you're done, you spend a lot of time developing something like that in a Jupyter notebook. But when you're done with it, all you need to do is say run. And you can reproduce that work. And that's going to have a profound effect on our science, because when the cloud stuff is fully up and spinning at Earthscope, it means you could publish a paper with your pre-processed notebook at MsPASS and say, you could reproduce my results if you just run this workflow. It might take you a week of processing, but you can reproduce the work. And that will have a profound effect on what people, on the ability to reproduce what people do, which is really difficult, almost impossible today. Anyway, so now I'll move off course business, unless there's a question. Did anybody raise any questions about anything like this? Yes, no, say so. Okay. No? Okay. I'm going to give you about 5-10 minutes about a sales pitch, basically on MsPASS, what it is, overview. So the name is an acronym that stands for Massively Parallel Analysis System for Seismology. That's what the acronym stands for. But some things about it is, this is our first little discussion thing I want to spend a few minutes about. I think a really important thing to recognize about what MsPASS is and is not is that it is a research computing framework. The keyword is not framework, but research computing. Can anybody here articulate what they understand about what I mean by research computing, as opposed to another term you might have heard called enterprise computing? Anyone want to jump in and say something? Just unmute yourself. Be brave. Come on. You might not have thought about it, so I'm giving you a little time to think about it. No answers? Oh, a silent bunch. I got to work on that. Okay. It is important to realize this distinction in anything you work with in the IT world today. And that is, there is a huge difference between production or enterprise software like Zoom that we're using and a whole string of other things that's on that computer that you're listening to me with that are what are called enterprise software. And that's really hot, lots to low level things like all the stuff that you use every day nowadays when you use a computer. But it also goes all the way down to specific things in the science that are really made to be where the critical difference really is that to be a enterprise software, there has to be a market for it, and it solves some specific problem, and often usually the performance is a really big deal. That, for example, oil and gas seismic reflection processing, time is money, and the more efficiently you can do that processing, the more money you make. Whereas in a research problem, that what happens, every problem is a little bit different. And so to have a research computing framework like MsPASS has to be very flexible, because that's to solve a range of problems, because as flexible as possible. And I say performance is important, but it's secondary. As long as something is feasible, it's good. It's meaning you could do it within time to complete your PhD degree or whatever, or the time of a NSF project. That's feasible, but it often is just a one-up thing. It's like, I want to test this hypothesis, right? So it's not the same as running something over and over and over again. And it's really a fundamental difference of something like MsPASS, that as opposed to some other examples here in a minute. But anyway, the other two differences that it has, enterprise software has to be done by anybody with minimal training, because the company doesn't want to spend a lot of money on skilled labor to something that takes an expert to run. Whereas a piece of research project, we make assumption that you are a lifelong learner and you're willing to dig into the guts of this to make it work, that you solve a particular problem. So it's not as user-friendly. You got to deal with Python programming in our case, right? So the last point is that in the case of enterprise software, the data is usually fixed. What it can handle is fixed by the application. Whereas in research, the data you're going to have is very variable. And what you want to do with it is different. And so you need a much more flexible system for doing that. And so, for example, one of the really, in the MsPASS case, I'll get to in a little while, we'll work on today, this database system we call MongoDB, I say is absolutely the perfect research database system, because it is so flexible. You could pretty much throw anything in it and it could manage it. Whereas if you've ever worked with a relational database system, you know the walls that you encounter. But anyway, we'll talk about that later, I think. So a few other things. What is it good for? Well, it's actually the only game in town for what I would call big data problems. There is nothing else like it in our community to handle seismology data. There's things for handling seismic reflection data, but not generic seismology data. It's mostly a thing with a bunch of tools for assembling low-level event-based data, but it can handle continuous data. And there's a fairly complete set of, just because of Ian and my interest, there's a quite complete set of stuff for P-wave receiver function processing, but that's just an accident of our interest. And there's a bunch of stuff for spectral estimation because of related stuff. But to add more to this package, it's easy to do. The community has to contribute, and it can, because it's an open source package. I'll get more to that in a minute. But what is it good for? More about is it's a generic processing toolkit, waveform processing toolkit. It's mostly about waveforms. The MongoDB database itself has a lot of flexibility, and I've used it in some weird projects. Like at the moment, I'm working on a project with a structural geologist to handle geologic map data. And it works great with MongoDB, but it has nothing at all to do with seismology. But the database works great for it. Okay, anyway, it's the scalability is probably what makes MsPASS the tool of big data. It means that you could prototype something on a desktop with this one processor or multiple, or one or two, get it to work, and you could scale it up to as big as you want of processors as you could pay for or get access to on an HPC or a cloud system. So if a problem that might take, for example, the problem Ian and I are working on, I estimate would take about a year to run serial. We could run it in a few days with enough processors thrown at it. That's a difference from a problem that's not feasible and one that is. And so this parallelization part of MsPASS is what makes impossible tasks possible. The data management system that's integrated into MsPASS is essential for big data, because my rule of thumb is if it's more than about 1,000 things, it's impossible to keep track of it without a database effectively. And so it's really essential for a big data problem to do that. And the thing I already mentioned about reproducibility with notebooks. So a few things it's not. There are some problems in our field that we considered solved that we intentionally avoided, and they're listed there. We don't want to reinvent the wheel. Okay. It's also, like I said, not a complete solution for everything. It's a framework. It's pretty much a complete solution only for P-wave receiver function processing. Anything else, you're going to have to do your own some part of the problem. But we provide the tools that are the low-level grunge crap that you do not want to rewrite. We spent 6 years on it now, and it works really well. The other thing is it's not a commercial product. It's 100% open source free, because it uses a bunch of stuff. It's not everything. We've concluded open source stuff from a lot of packages that is in this package, which makes it quite complex. But it's blatant. It's militaristically open source, and everything is completely, nobody has to pay for anything. But its future, because of that, because it's the open source model, means that this community has to support it. And I say that I'm 72 years old. My lifetime to be able to maintain this hopefully will outlast me. And I will not live long enough to be able to keep maintaining this package. So somebody has to replace me. So anyway, I'm going to skip this slide to get moving on here. I think it's important to realize that there's some things in here that you can read later. There are just some details. I think it's really important to realize that MsPASS makes certain packages that a lot of you may be using completely archaic. SAC and an old package at Lamont called AH are total dinosaurs, and they should be avoided. It's just that people have all this legacy stuff that uses this stuff. I also would claim that MsPASS largely supersedes OBSPI, because I have another slide on this in a second, but whoops, in fact, let me go back to that. So I'll come back to that one. The other one that's important to realize is that the sales pitch is that it really is rock solid. This is the first time I've taught this class that I can say with confidence that I couldn't have a line here that says it's not bug free. Well, it's not bug free, but it's pretty darn stable. Like I said, I haven't had a seg fault 3 years, which is a sign of a really bad bug. And all the errors I ever get anymore are usually data problems, or something didn't handle it the way I thought it would. It just runs, but it may not behave the way you want it to. And that's what you want with a package like this. It's true of seismic reflection packages too, that usually there's an iterative process that you have to go through to get it right. And that's where this works now. My last slide, I think, is about OBSPI, which is that if you're an OBSPI user, you could just as well use MsPASS, because it's true that MsPASS is a superset of OBSPI. It operates with some concepts that are very different you'll learn about this week. But it's really pretty straightforward to convert almost any OBSPI Python processing script to a MsPASS script. There are some differences. It's sort of like converting between two languages, which are dialects, or not quite, more like Spanish and Portuguese or something, which are pretty close together, but they have to be translated. You can't necessarily understand it, but if you know both languages, you can translate between them pretty quickly. So more that's enough. I was just repeating some things I said before. Probably the most unusual thing you'll find, and we've spent a lot of time on for a package, part of what the 6 years is documentation. I would say that of anything that I have ever seen that has a user base the size of this one, which is just the seismology community, I think there's no package that's better documented. It's better than commercial packages that are used in our field by a lot. If you haven't discovered it yet, here's the user manual, if that works. And I'm going to refer you. I've got various things in the homework to look at some of these things. There's a lot of pages here. So there's a lot to read. So there's others. If you have a problem, it's a good chance it's addressed in here. I'm going to point you to one thing that's actually particularly useful right now because I got this page up. The algorithms page, which is what you use to design your workflow or what you need to do something. This is a fabulous summary. And the way we have it structured, that all the algorithms, all the functions that exist, processing functions and different stuff within here. But these are all hyperlinks to a docstring page for that particular algorithm. Not a very good example because it's, some of them are pretty cryptic, but that's the point, is that to get to the, back to my point, is that there's a lot of material reference on this. The only thing you have to do is spend the time to read it. And there's also the resource of Ian and me. You can always contact me, and I'm happy with any student in this class to follow up as long as you want to. Send me contact me by email or whatever. Say, I don't know how to do something, and you tell me how to do that. I will do what I can. So finally, I'll stop blabbing. Wasn't too far off what I expected. We're going to move now to this notebook. And these are the topics that are in it. So let me jump to that, which should be here, I think. Yes. So while now is a good time for a question answer session. Do anybody have anything that came out of there you want to address right now? Otherwise, make sure everybody should bring up this page because we're going to be working through this notebook. Where's the Q&A? Is there anything? That was mostly a sales pitch anyway. So going once, twice, 3 times. Okay.
Hello, I
Yep.
have one small question.
Yes.
When I tried the line for using the Mongo database in the terminal, apparently it's not installed in my environment, which is kind of weird. But all the package, everything works except this one, which I don't know what's the source of error, how to handle these problems.
When I had that, I had the way this is what you should see happen. When you launch it, I was just going to say, this is what you do. You launch a terminal like this, and it should be from the home directory. You launch it this way. When I had that happen, Mohammed, when I had something like that happen, I just screwed up and selected the wrong tab when I launched the server. If you don't select the MsPASS, I can't go back to that without a big delay. But if you don't select the first pull down, which says MsPASS, it says GeoLab to start. If you don't select the one that says MsPASS, you won't see MongoD because it doesn't exist on that container that's run when you run the regular GeoLab. So that's probably what happened. Are you running now?
Not now. I can run it within a few minutes, but
Yeah, why don't you restart? Sarah, can you remind me how you restart? I don't remember. I had to fish around for it. It's like one of these things up here.
If you go to the File menu, File,
There
Hub
it is. Yeah,
Control Panel, Hub
yeah,
Control Panel's near the
there it is.
bottom,
Yeah, see this
and
one
then
here?
hit Stop My Server.
Yeah, that's almost certain that's what happened. Is that you didn't select that right? It's easy to do because the default, it's just if you're kind of jumping in quick, it's easy to. That's good lesson to everybody. So, and when it does work, you should get this echoed to you. That says it. Well, the first time you do it, you won't get this, but every time you should all get this message because it's telling you that there's already a log file for MongoDB, but it's running. Anyway, and by the way, while we're here, I can't see it because I'm in a different directory, so never mind. Anything else? Okay, so everybody should see what I did right here. If you haven't done this, you need to do that to get this to work. So, like I say, all these notebooks you could read after the fact. And if you're not following me, you could. In fact, that's the quiz will ask you sometimes to go back. If you don't answer the question, go back. If you can't answer the question of the quizzes about this exercise, go back to the note. You should have the notebook there anyway. It'll help you answer the question. Because I try to explain everything before we do it. So the first section in here is that everything in MsPASS that you might find foreign, everything in MsPASS is driven by the database. And that's why I had you generate the test data set, because now you can see how you work with this. There's this kind of grunge work to put the data set together. And every previous times we taught this class, did that, and I realized that was a terrible way to understand how this works, because that's the grunge work to get it together. This is what you really want it for, is that once you've gone to the work of putting it together, you can do this stuff. Okay, so anyway, here's the first point is how do you connect to this database? I had in my pre-course lecture about databases, I talked about database servers and that kind of stuff. So what we have to do in this first box, when it runs, we have to run that. It generates a client for the client server. The server is running. You launched the server when you ran that MongoDB command. That launches the database server. Now, on this notebook, we have a client, which is the client that talks to that server. That's just a standard arrangement because by having a client server, there's a lot of good advantages that it's everywhere in the modern world. You talk to so many clients and servers in everyday things you do on your phone or whatever, and you don't even know it. But it's like one of the most ubiquitous things in modern computing. Anyway, so what we just did is created, if you read that box, which you should, DB client is now a handle to the client itself. It's defined, but what we're going to want is a handle to our database. And the one we created is called EarthScope 2025. And it's instantaneous to do that because the client already knows about it. It's just, so what I now have this symbol DB, which is a thing I always use, is the database handle. DB client, remember, is the program, if you will, that's running, talking to the server. But DB, it can talk to more than one database. So you could actually have a different symbol, DB2, pointing at a completely different database, and it'll work fine. Each database's top level is given by a name, which in our case is EarthScope 2025. So the first part of this session I wanted to go over is actually kind of deep in the weeds, but you really kind of need to understand it. And that is the way we keep data. The data in MsPASS is fundamentally waveforms. Everything else is secondary because the whole point of MsPASS is as a waveform processing tool kit. So the core data type are seismology data types, and there are 4 of them. 2 of them we call atomic, which is what we call a time series and a seismogram. Now, a time series, we created them in that workflow. So if we look at this one, that just did a lot in the time it took to just click it. The first command is a database command, find one document. We'll get to that later. But then all we need to do is to say read data with that template, and I got a datum D, which is a time series object. What's in that? It's a seismogram. Well, it's a time series, which we define as a scalar data. So there's a single channel of data in MsPASS definitions is a time series. And this little box plots it with matplotlib, which a lot of you probably know if you've used Python much. And all we do is the x axis is time. So we use this time axis method, and we can access the d.data. D is the symbol, it's the time series object. It has an attribute called data, which is the vector of data. Yes, Tammy, you got your hand up. Somebody has a question?
Hi, I'm sorry to interrupt. We're watching the back end and we are fluctuating with the number that are in the wrong image. We want to make sure that everyone can participate and follow along with the notebook. If you are getting an error on MongoDB or you're not seeing the notebooks, you need to do the file, go to the control panel, stop the server, and you need to have selected the MsPASS. You can look in the chat window to see the 2 settings that you need. But we're watching still that fluctuation, and I just don't want anyone to get too left behind. So if you are seeing errors, not seeing the notebook, now is the time to log back out of the system and select repeat the process to log in, but select MsPASS short course.
Yeah, the good thing about the course today, actually another nice thing about this notebook too, but you just raised this point, is that it's really lightweight. All we're doing here is just really simple stuff today. We're just kind of looking at what the data is. So all this, it's easy to catch up. In fact, you could run this whole notebook once you get going, and then I'm just doing it one by one because we're going to work our way through it. You could run the whole notebook and recreate all the outputs of it. Okay, thank you. All right, so where was L? So again, the x-axis is time, and the data value is a vector of data. These are actually, you could pass this data array to NumPy, for example. There's a whole section of the user manual about how to do that. If you know about if you use NumPy much. One thing we spent, or mostly me, spent a lot of time designing this objects that are MsPASS, and I actually would argue that it's a step above what the people at MsPASS did 20 years ago. Because this is about the 3rd version of what these is in this data that defines these data objects, a time series. It's first fundamental. Everybody should recognize, anyone in seismology should recognize that there are just some fundamental things. These are the fundamental attributes that are the only core things that you absolutely must have to be able to define any single channel of data. Everything else is metadata. What they are is you got to know how many points there are to know the length of the vector. You need to know what the start time is. And that means 2 things, like what is the first sample's time and what does that time mean? Is it in seismic reflection processing, sample 0 is always shot time. In earthquake seismology, it's almost always a UTC time. In MsPASS, we have a rather we have a way to switch it back. There's a week UTC in relative time. So lots of applications where you don't want to be at UTC time. You want to use a relative time frame. And we'll see some examples of that in here. But that's pretty much it. Everything else is metadata. So what we do, we'll see in a minute, is that we actually put that stuff in a container that looks like a Python dictionary. That we call metadata is mapped into a container there is a container called metadata, but it acts just like a Python dictionary. It is not a Python dictionary, literally, because it's implemented in C++ at a low level in this package. But it's as fast as a Python dictionary because it's implemented in C++. Anyway, the next thing I want to talk about is we also have a different thing we call a size. Oh, there's a hand. Yes. Go ahead.
Hi, yes, sorry, just about the graph up there. So it might be a bit repetitive, I'm not sure, but just to understand it well, I understand the points on the left are the counts. If but on the x-axis, the time starts from which time? Is that the right like time from number
Yeah.
of seconds since beginning of the day or something?
No, it's actually that's a good point. It's actually in here. If you follow that link there about time in the manual, but a fairly universal practice in all of IT is to store times for efficiency, not as a timestamp. Like a date string is a horrible way to store times. The computer likes the data. You can store them in a single double precision floating point number. It's called Unix epoch time. It's like the number of seconds since 1960, January 1960 or 1970. I don't remember which. I think it's one or the other. And that's exactly right. Is that we store it as an epoch time. So it's a huge floating point number, is the number of seconds since like 1960. And that just makes all calculations of time differences really fast. Because you don't have to sit there and take apart it. Otherwise, if you had really literally stored it as a date string, you have to start taking differences between them. MsPASS has this too, actually, but they call it a timestamp in the UTC date string or date time or whatever object. They have a timestamp. It's the same thing. Okay.
Okay, thank you.
Okay, good. So a seismogram is a concept that's been used in a few seismic reflection packages, but it's kind of unique to MsPASS. It's essentially a bundle of data bundled into a three-component object. So if you have a three-component system, which almost all modern seismic data is, you have north, south, east, west, vertical. You want to keep that together, and it's actually a lot of work to put it back together. So we have a special object we call a seismogram object, just because it's kind of vague, but originally it used to. At one point, my library called it a three-component seismogram, but that's too verbose. So we call it a seismogram. But it's essentially the same thing as a time series, except that the data samples are vectors of three numbers for each sample. And so the way we actually store it internally is as a three by n point number of points matrix. And that matrix could be manipulated in NumPy. If you know how to do it correctly, there's a section in the user manual about how to do that, or with tools that are in it directly. And in Python, standard tools for manipulating arrays, colon notation and such. You can do all that kind of stuff with the matrix of data. So let's just do that. So to show you that it's we created seismogram objects in that workflow. And so we're going to do essentially the same thing here. Find one, It's the same thing I used in the one above, only this time I'm using a different name here, WF. We'll talk about how this works out in a second here. WF sizeogram, and we're going to read the data, and I have to tell it that it's in a different place than the default of time series. And I just read it, and then I use a little bit different plotter because there's no easy way to plot in matplotlib. There's not such a simple way to plot a 3-component sizeogram because it's a matrix. You could plot it as like an image or something, but it'd be weird. It would be useless. So we're using here I used our native part of MsPASS graphics called a seismic plotter, and this is just a default plot it produced. So this is just a repeat of what above. These are the core attributes of a sizeogram. We have to add some things. We've got a number of points. We got time 0 at the time reference. But the big thing it has to do is that the data type, like I said, is a matrix now. But we also have to have a transformation matrix. Because if you're going to properly save and maintain a 3-component set of data, it could rotate, or you could reorient the coordinates, or it might not even come in right. So in this case, this is the transformation matrix that when this thing ran, that's what it created. And that is, ideally, if the data are, quote, cardinal, meaning north, south, east, west, vertical in our convention, that transformation matrix will be an identity matrix. So this matrix that's shown here would be 1, 0, 0, 0, 1, 0, 0, 0, 1. It ain't that. And the reason is that the data were not ordered by east. There's 2 reasons. One, they're not east, west, north, south, vertical order. And the second one is this is TA data where they measured the component directions exactly. So there's a slight rotation of the horizontals. So this matrix here is as a scrambled small rotation around the vertical axis. So we'll look later, we're going to use a method to return it back to cardinal. We can do that. There's a method of sizeogram called rotate the standard, which is a horrible name, but it's historical. That puts it into cardinal directions. But you can also transform, you can do any kind of rotation, transformation, those kinds. They're methods of sizeogram. So that's a really useful feature of MsPASS, because if you're doing anything with 3-component processing, it's all built in. You don't need to find a gazillion different functions to do what you need to do. It's all methods that are capped and they're packaged up with this object type. So the last thing I'm going to do before a break here, which is going to come out to be just about right. Man, you learn a few things in 20 and 40 years about how to time a class, I guess, is what's called an ensemble. Now, it's a little confusing because there are actually 2 types. There's a time series ensemble and a sizeogram ensemble, which means that if you've worked with seismic reflection processing, you know the same concept. It's called a gather. So if you've ever taken a course in seismic reflection processing or worked with a seismic reflection processing package, you might have heard the jargon terms source gather, CMP gather, or common receiver gather are the 3 most common ones. We essentially generalize that in MsPASS as what we call an ensemble. An ensemble is basically defined however you want to define it. It's just a group of data bundled together. I'll say that again. It's just a group of either time series objects or sizeogram objects that are bundled together. And it's up to you to make sure you know what the relationship is. And it's a really useful thing. And like, for example, we're going to work with source gathers. So things driven by event, the things we created were event data files. So it's natural to bundle them up by sources, by common sources. So let me quick run this guy. This will take a little bit longer because it's got to read 1,000. It's reading 1,000 seisograms, time series objects actually, and then it's going to plot just 10 of them. The reason it goes black here, by the way, is that that's the S wave. It's actually something comes in that just wipes out everything. I don't remember what happens here, but anyway. But what the idea is, this is actually only this thing right here is what limits the size. Otherwise, it was that big. That's a lot of data. 1,300 channels. It would make this whole thing black if you tried to plot 1,300 wiggly lines in that little panel. It would all be totally black. So I just pulled out the first 10 to show you what they look like. And they're a mix of channels and some good data and some shitty data. But that's typical, which you'll find. I'm just grabbing stuff randomly. So this is just showing you using the Python type command. It says what read this. The way we did this is just like before, that we're using this read data method. We'll talk about later in the second part, half of the day. But we do a little bit different here. Instead of saying find one, we use this thing, which is a MongoDB construct called find. We'll talk about this more in a little bit. Return something called a cursor, which again we'll talk about shortly. That just means it's a collection of the things that define this group. It's driven by a query. We'll talk about, that's what this afternoon's session is going to be about. But the main thing is it returns this thing. You tell the reader, the MsPASS reader, read that data from me, and it loads it all up into this container called an ensemble, time series ensemble. And that's just a really useful way to work on data that has a common relationship. So for example, there's a multi-channel array processor that's newly introduced in MsPASS. You need one of these. You load it into this ensemble, and it'll do cross correlation and stacking to get a correlation timing for every seismogram that's in the ensemble. So this is just telling you that it shows that it's their time series. The name of the type of this object is a time series ensemble. Inside the thing is another container, which is the wrappers called a time series vector. The point is that member, I want you to understand, we'll look at this a little bit later, but member of the symbol E in this code is the data of the entire ensemble. You could point to an individual piece of it, but through this attribute called member. And member is subscriptable or iterable. So you could work through the members of a time series like this. So this is an example, just it uses Python constructs. How many members does this have? It only has 10 because I only limited it to only 10 of them. And we could, what we do here, I could take one of them out. This is how you look at one. So I just grabbed, I say it's subscriptable. I can take out member 3, arbitrarily pulled out number 3 from the ensemble, and I can plot it like a time series. So when you use this kind of construct, you can pull a single time series out of the ensemble to work on it, and then you can put it back in, or just work on it directly. But that's a detail. So that's the purpose of these ensembles, are a way to basically a way to bundle data together. Of the atomic data are time series and seismogram, and there is a time series ensemble and a seismogram ensemble, which are bundles of those two atomic types. And here's the last topic, which I'll quickly do here. I'm going to run these 2 cells. Is metadata. What we store in MongoDB is, we'll talk about Mongo here in a minute, but is Mongo actually stores what it calls a document, but a document is a silly name, or it's actually just an alias for Python, Python dictionary. So what we do in this case is I'm going to just say I'm going to retrieve this thing, find one, the same thing we read data from before, and I'm going to use this function called print metadata to make it look pretty. But this is what's metadata for that first document, for that first that used to construct that first one we looked at the very top of this notebook. There's a lot of stuff there. But everything in it is a Python dictionary. This actually is a Python dictionary at this stage. They're key value pairs. The key is like this, a channel PHC. So the thing I want you to understand right now is that MongoDB stores essentially Python dictionaries. We put them in the actual data objects contain a metadata container, which is identical. If you print them, those two things are identical. They can be switched back and forth from each other. In fact, and you'd lose nothing. You can take a metadata container and turn it into a dictionary and vice versa, and nothing is lost because they're just two different data structures that do functionally something very similar. There's minor differences, but the only reason that metadata exists as a separate thing is because it's easy. It was useful for the C++ components of MsPASS that are in there for speed to make the work more easily. Otherwise, Python and C don't play well together. It's better to have them totally separated from each other, but that's a detail. All right, so we're going to take about 5 minutes, I think, for a short break, and then we're going to go on some things about MongoDB. So does anybody have any questions that came up right now before we move on? Anybody want to ask a question we have? Or while you're thinking about that, I forgot to do the last cell, which the point of that cell was that you could manipulate a data because the data, I forgot to mention that that both seismogram and time series objects use the concept of inheritance and object-oriented programming. And what it means is that because the data objects is a metadata, or it acts like a dictionary. So the things that are in the metadata actually act like a Python dictionary. So you can use Python dictionary constructs like this on data objects. A seismogram, D points to a time series object. So you can extract the values as key value pairs just like you would a Python dictionary. It's a really nice, handy API. It's different from MsPy because MsPy chose to put that kind of stuff is in a separate attribute called stats. It's a matter of opinion about which is a better model, but this is the way it's done in MsPASS, so you need to know that. But any questions? No, I don't see any hands raised or talking. Okay. I want to go next then to for a few minutes, a little bit of some basic stuff about MongoDB before we dive into the hands-on part of this. And so the first point is that metadata, the thing we talk about metadata or Python dictionaries are a very different thing than the sample data, mostly because of size. And that is that if you look at the size of the data occupied by the dictionary part, the metadata of any object I've ever worked with in MsPASS or any processing system, the metadata is a tiny, tiny fraction of the waveform data, sample data stored in a vector or a matrix in our case. So they have to be treated very differently. And it is important to realize one thing I want to emphasize here is that the way we use a dictionary like this is, in the same way MsPASS does too, is really is a creative, different thing from traditionally of what is called a header. Yeah, someone has their hand right. Go ahead. And bro, whoever that is.
Yep. Sorry, that's me. Sorry, I joined later. I just joined in. I was trying to follow up for the session 1, and I tried to fire up the Mongo database command, but it tells me MongoD is not installed.
Oh,
I couldn't, however, figure out how
yeah,
to resolve this.
yeah. Okay. I will repeat what we said when we started. I had someone else asked the same. I think it was Mohammed had the same question, had the same
Sorry.
problem. What you have to do, I made the same mistake myself, so I know how to fix this instantly.
Awesome.
You have to go back to. Let me just show you this. You'll have to go back here and restart Hub Control Panel and stop the current server and restart it. But you got to select on the very top pull down. You have to select MsPASS because the default GeoLab container that's being run by default, if you don't change it, does not include the MsPASS extensions. And that.
Oh, I see. Yeah, that was my issue. Yeah. Okay. Thank you.
Anyway, yep.
Sorry for holding you up.
No, you missed the statement. Said that the questions are more important than anything else, and it just reinforces that that's an easy mistake to make. I mean, I did it too, and I've run several times. Like, oh crap, I forgot to select the right one. It's when you jump in, you're going to hurry. It's easy to do if you overlook it. So, anyway, there are actually two. There's another element that's different about MsPASS than MsPASS. That's essential for running in a large parallel environment, which was designed to do. And that is that when you're running in a big HPC job or a large cloud job that runs for days or whatever, you cannot have it abort. It turns out the things it's kind of my design idea. My opinion, it's kind of a design flaw of the things we're going to use for parallel stuff. But if you have a function that throws an exception, it will abort the entire job. And that's bad if you have something that's going to run for a week and suddenly it aborts on a data error that it couldn't handle. So what we do instead of throwing exceptions, you have to wrap. What we did with all the MsPASS stuff was we had to wrap the functions in an error handler, and instead of throwing an exception, it catches the exception and writes it to an error log or container that's contained inside the object. So what it does is anytime an object you have an error in a processing in a function, it posts an error to the error log, and that goes with the data and it carries it along. And that allows you to work with millions of things when you can guarantee that thousands of them are probably going to have problems. What you do is then you just log them as an error and say, this thing's bad. And we'll get to that a little bit here. We actually use what's called a kill. Most functions will kill something that it could process. And it'll mark it as bad. And then it will put something in the error log. And that's an important feature of MsPASS that's why it's a weakness of MsPASS. It will not work on without this kind of thing. So what I have here is just to show you that an example of how you should think. Bad fumble fingers. Okay. I don't know if this is in the way. In my case, it's a little bit in the way, but this is the kind of thing we did in the end of that last session in the notebook just a minute ago. This might be the contents of two different data in this beast, and this thing would be the I'm pointing at here is the metadata that would map into the data this way, into a metadata container. The sample data is stored as a vector that's inside. This white is the object, the sort of the thing that's the data object. But it has this error log, which contains those error messages if they get posted. It also has a thing I'm not going to really talk about today, which we haven't really exploited fully, but it has a processing history thing that will keep track of all the processing steps that have been done to any given datum. The capability is in the package, but we're not going to really talk about it in this class. It's there, but it's kind of something that's kind of designed as the topic we had about reproducibility of workflows. Anyway, so we're going to talk a little bit about this. And I talked about, I think, in that pre-course lecture about CRUD, which is every database has to be capable of create, read, update, delete. We're going to talk a little bit today, mostly focused today on create and read, which is like read data, or write data, or save data and read data. And we saw some of these, find one and find and read data. We already saw examples of those. We haven't used these yet, but except you use them when you ran that workflow. You'll see that'll appear, and then we'll come back to the end of the day. We'll talk about that. These are like MongoDB commands. So what I want to talk about is what happened when we do a save, which is in this workflow that we used. As the inverse is read, but I have this I'll do for save. Oops. It has what the important thing to realize is that there are these different pieces. There's the metadata, the sample data, the error log, and the processing history. I just showed you is what the object has to have. And this little wiring diagram emphasizes what you has to do as a reader or a writer. Is that the construction of the object that we work with, if you're reading, is driven by metadata stored in MongoDB. And that's these things, you saw these symbols, WF time series, WF sizeogram, we looked at a few minutes ago. We saw in there, I referenced those magic words. Those contain Python dictionaries, documents in MongoDB jargon, that describe how to reconstruct a particular datum. In most cases, that means that it has in there something like, we'll look at some details here in a minute, like a file name and a directory place, how to read the data, sample data from a file system. It has MsPASS has the capability inside MongoDB of something called GridFS, where you could store this data internally, sort of like in its own internal file system. We have found we do not recommend it. You could do it. It's actually nice for convenience for small data sets, but it is really slow. Not really slow, but it's slow because it has to go through the same channel, I/O channel, as the metadata traffic. And so it tends to be bottlenecked rather easily. And you could completely throttle a large workflow by putting your data on GridFS. So all the examples we'll see today read and write data from files. So database, the read part of data of CRUD is the query problem. And it's actually, if you've ever used a database explicitly, one of the things that I think I've said more than once is that you almost certainly use mini databases every single day on your phone or working on your computer on various websites, because that's what everything's controlling everything. But most of those are relational databases underneath. MongoDB is a little bit weird in what's called a document database, and it has most relational databases use a standard language called structured query language, SQL. MongoDB does not understand SQL. It has its own peculiar dialect, which is one of its weaknesses, but it has to be because SQL has embedded relational database concepts. So SQL is what it is as a language because it is tightly coupled to relational database concepts. MongoDB is not that. MongoDB is this weird thing called a document database. We'll get into here in a minute, but a critical thing is that the query language is essentially Python dictionaries. And one of the weird things I've found in reading all the documentation, lots of documentation on this, is like people don't state the obvious when they start talking about how to do things. They just give examples of MongoDB queries. And they'll tell you that the first rule is that almost everything you give it is a Python dictionary. They're like key value pairs, and we'll see examples here in a minute. But there are actually two different methods. We saw them both in that little example we already looked at. Find one retrieves one record. In MongoDB jargon, a single record, the atomic level of what you pull out, is called a document, and a document equals a dictionary. It isn't literally, but when the PyMongo, the interface API, when you retrieve something with find one, you are retrieving it into a Python dictionary. So the output of find one is a Python dictionary. Find is a thing that retrieves mini documents. So it returns that as a thing called a command cursor, which we'll talk about. I think it's better to see it as an example what it is. If anybody who's worked with a relational database have command cursors. It's a concept that's used there too. It's just an iterator that you could work through a group of things, a group of documents. That's a better way to say it. In fact, that's worth saying right now. A command cursor is just an iterable that returns a sequence that, if you iterate over it, will return a sequence of documents. Each of which is a Python dictionary. I will say that I find the online documentation for MongoDB totally sucks. There are books that aren't bad. I have a book that I learned a lot by buying the book. You can look at my words. You can find out. You tell me whether I did it well or not. But this, you should follow this link and looking at some of this, and it tells things in it that you'll not find anywhere online. The rules of the language. There's nowhere else I found anybody specify the rules of the language. So it's in this section. I'm not going to bother you with it today. And the tutorials here are good. And a similar tutorial last year, I went a lot longer in this same class. I spent almost the whole period, 2 hours on MongoDB, and I got a little too tedious, I think. So, but it has a lot of useful examples in there, so you can follow this link in this PDF later. We're going to look at some constructs like this. I don't want to dwell on it right now. I want to go back to the notebook. But basically what you do is what I want to just show you is this is a typical way you do things. You could get a command cursor from find, and then you loop over the cursor. This is an iterator for doc in cursor. So what it says is you're going to loop around and retrieve a series of documents, dictionaries, read data, takes that document and constructs a time series, in this case, from each document sequentially. Then you can do processing steps, and then you typically save something. That's a typical, what I'll call an atomic read loop. So a serial processing loop with one processor. We'll look at parallel versions of this later, but that's kind of our prototype. Whoa. Hit the wrong button, but well, I'm done anyway. Ensembles are a little different. They're typically driven by the grouping. If you're going to do processing driven by ensembles, we have an example just like this in the workflow you ran. This first line here says DB source find is actually in the same workflow ran, it says it keeps a thing called an ID, the ID for each event in the database. And it's going to return a list of those magic ID numbers. And this is generating, then you're going to loop, the iterator is going to be over the source IDs. That's a small number of things. It's not a giant thing to say or store in memory. But this is a typical ensemble loop. So you loop over the whatever the grouping criteria is going to be. In this case, source ID. You construct a query. We'll talk about this language. There's an example of what I talk about, Python dictionary. The query language uses a Python dictionary. If you don't know how to, are familiar with it, this is a inline construct of a one key value pair, source ID with the key source ID, and the value you insert in it is SID, which is the iterator for this loop. And then you run read data, or you say find returns a cursor with that that query for that group of documents. And then you call this read data on the cursor, which will bundle it all and return all that data in a single container called the time series ensemble in this case. And then you process on it and you save it. That's a typical ensemble serial loop. Okay, so where am I? Oh, somehow I got over here. There it is. Is it? Where am I? Maybe I'm on the wrong document. Over here. Okay. Questions about that? We're gonna go over this kind of some of this stuff a little more detail right now, but going once, twice, 3 times. Okay. Oh, go ahead. Yeah. Go ahead.
Sorry, are we supposed to speak up? I might have missed that, or just raise a hand for questions.
Well, you raise your hand but in this case, when I'm asking for input, speak up. Yes, just speak up in these kinds of sessions. Yes. Go ahead.
I was just wondering if the saved data will overwrite the previous data, or if it is saved as a copy in the database.
Never. Never ever overwrites anything unless you really force it to. In fact, if you try to write sample data to a file, it automatically checks the existence. And if it exists, it will always seek to the end of the file and write. It never, you have to explicitly delete data. There is a delete section. And you could clean out files with it. It's kind of a slow way to do it. It's kind of, we're into a bit of, it's a good question though. It's a really good question.
Okay, but is there danger then to blow up the database by just processing over and over and storing over and over the waveforms?
It's not the database that could explode. What you have to do is, the database compared to what the waveform data typically is tiny. Because all we store is the metadata. And so the waveform is what data can get bloated if you don't do house cleaning. So, an for example, in this, we had a discussion about this for the structures of the class. It's like, well, this workflow is actually a little bloated because I don't clean it up. What you generated, you keep a copy, you keep the original mini-seed data, you keep a copy as time series, and you keep a copy as seismogram data. So there are actually 3 copies of the data in that you processed. So it can get it's really better to clean up behind yourself. But typically you often want to do that, what I did here, which was to save intermediate steps. But it's really disk space that's more gets you into trouble if you have a large data set. You got to be careful that you're not going to exceed the bounds. But that's an excellent question.
Okay, thank you.
Okay, so reiterate, this is actually coming back to the beginning, which is that the database object that we created at the top, where we said DB equals get database, whatever, it's a monster. Okay. But most of what you have in here, well, the database object, this handle is an extension of MongoDB's database handle. We added some things here like read data, save data frame, read inventory. If you compare, a lot of these are, some of them are MongoDB, some things are ours. But what I just want to say is all those methods that are in there are convenience things for seismology data. So like save inventory is a way that we'll see how we used it actually in that workflow to save data, station data, metadata we downloaded from web services with HubSpot actually. So the first thing about MongoDB that you want to know, I've talked about documents. Documents are the lowest atomic thing in MongoDB. We have the other end member, which is the database name. So we had a database, our database name, I don't want to go up there, is EarthScope 2025. That's the name of the database. DB, the DB symbol points to that database. Okay. In between is MongoDB's construct, what it calls a collection. For anybody who's used a relational database, a collection has the same significance as a relation or a table, but it's not a table. It's a grouping. It's a group of related documents or dictionary or Python dictionaries. The expectation is that things that are in a collection have the same keys, or they don't have all the same keys, but they share a syntax, or they share, not syntax, the wrong word. They share the meaning of what a key is. You know, if stay, STA, in waveform, in all our waveform collections, means the station name. Net is the net code, etc. Time and start time is the start time in of the first sample of data, for example. So I reiterate that it's like a collection has data, a lot of documents in it, but the expectation is that they have the same keys. Some can be missing, but the names are always mean the same thing. Or if you use it in two contexts, you are screwed because you're totally screwing up everything, because that's all it could use to distinguish one thing from another is the value of that key. So you always have to use them consistently inside the same collection. One thing about MongoDB, though, is it does not enforce a schema, if you know that word from relational databases. You could put anything in there. We have a mechanism in MsPASS that I'm not going to talk about to be pedantic about a schema, but we don't use it by default. So you could turn it on to be real pedantic about what it keeps and doesn't keep, and to check things. But I rarely use it. But anyway, that just the schema assures that the key always is used the same way as the whole point of doing it. And it has the same type on the right-hand side. Anyway, so let's look at what we have in this database. We have all these collections. We looked before at this guy and this guy. We saw it reference those names in those find commands above. And I don't know if we referenced Miniseed before. So these are actually the three waveform collections. They all contain Python dictionaries that can describe, can be used to construct seismic data. The other one's source, we kind of mentioned, contains source data. The channel, these are names borrowed from Center for Seismic Studies schema, by the way, but channel is single channel data. It actually contains response information as well in this case. The site is a simplified version we use for seismogram data. The idea of channel response and stuff is a time series concept, not a seismogram concept. Because once you bundled it together, it becomes obscure. Because like, can you be sure that all three channels have the same response, for example? Anyway, that's an example. But anyway, they each have different names. We'll come back to this one. Cemetery is kind of a colorful name. When I talked earlier about in a workflow, you kill data if there's an error, and you log an error. Well, the things that are killed end up in the cemetery when you save the data. And then you can find out who died, who was killed by the processing. It's a feature we'll get back to later on in this. I think if we have time, I hope we'll have time. So here, this is just a repeat of what we did a little ago before, which is, it reiterates what I said before, which is, here's the structure, though, now you see of this query language. The first thing is the database handle name. DB, that symbol holds database, the database to Earthscope 2025. WF time series is the collection name. So this says, apply this method, find one. It says apply that method to the WF time series collection. So this dot symbolism in Python is the way to distinguish. We're drawing a hierarchy of class methods. But anyway, what this one does is just returns one document. So if you want to do find one, we actually had the same command earlier. It shows the content of one of these WF time series documents, the first one. It's actually the same as what was up above. Cite is we can look at a different kind. Cite is a different collection. It's just only this time we're going to use find, which returns a cursor, and illustrates what I was saying about cursors being a series of documents returned. So if you look at this code, it says I'm only going to use 2 of them, because otherwise I'd have like 500 of them come back, and it would go on and on in this work notebook. So for this tutorial, I only want to keep 2 of them, as this limit2 does. So that obscure symbol means find all. Don't do it. Don't apply any. Just give me the first 2. All this really is saying is, give me the first 2 documents in this database in what's called the cite collection. And so the cursor is an iterable into the database. Technically, it's a thing called a command cursor, but that's the data type of it, but it behaves like a list. And so you could use it in this kind of a construct, is iterable for doc and cursor. And what we did in this case is just print it. So it says, here's the first station. There's TA station 034A, channel, or no channel, this is 034A. Here's 035A. These are just, mostly they have coordinates. The cite collection is really mostly just to keep coordinates that are keyed by station names. Okay. So a bunch of words here. Are there any questions right now about that, about what I'm talking about? So this is kind of the read side of things, about collections of documents, is what I wanted to make sure you understood that distinction. What the idea is, again, that database, collection, document, it's that hierarchy in the walk down the chain. There are many documents for a typical data. There's one database name that links them all. One do you rule them all if you, okay? All right, question, all right. So we did this, okay. The next topic then is we start in on these CRUD operations. The workflow is here. Let me see what I got here. we have what I wanted. I guess what I wanted to say here was you can go back and read this some, but the workflow that ran this created these collections that we just looked at up here. All these names. The workflow you ran created all these, and there were special methods that are in that. We'll go if we have time allows. We'll go back and look at that. I want to try to do that because it creates. So there are some special methods in there that were in part of MsPASS to make this work. So, for example, we have a writer we retrieve data with MsPASS download procedure. Just use it for web services, and they create a thing called a catalog, and we say we save the save catalog. We'll save catalog objects in the database. And so there's similarly a save inventory for station data. We'll look at that later if we get whatever time we have. So let me move on here. This is you can go back and read that at your leisure. So what I want to point out is that workflow created this. The core thing it created was WF miniseed, which was indexing a bunch of miniseed files that the workflow downloaded and copied into your workspace. And it's a kind of a small data set, but not tiny either, 26,000 of them. And it makes an index called WF miniseed that just tells where the files are and how to read it. And then we can read them later. That the channel collection was created by save inventory. Site was saved by save inventory. That's the station metadata. WF time series and WF seismogram were created by the workflow. They're processed data. We'll go back and visit that later. But I just want you to see that that's the idea, is that collections organize similar types of information. The miniseed data is all that WF miniseed, all the information you need to work from miniseed files. Channel stores the station metadata, and we're storing the intermediate depths of results that are already loaded into the framework as WF time series and seismogram. So now we're into this. When we save them, there is this issue about where the data landed. So if you look here, maybe I should go back and look at this. I should be probably showing you this fact instead of just talking about it. We created the miniseed, WF miniseed was created by running this box. It was actually downloaded from, we'll talk about this on Friday. This is actually downloading the data off the cloud, basically. So at this step, you're actually pulling the data and putting it into your workspace on the cloud from the cloud. Here, we have the miniseed data. That's these files right here. But we run this thing to index them that builds this thing called WF miniseed. And this little method here of MongoDB is just to count how many of them are. And that's where I got this 26,200 some. Oops, I went the wrong button. Okay. Then we do some processing. Well, actually, this is where we load web services is used here to retrieve the station data. The event data is stored. Let's see, that was actually earlier, the built source. It was driven up here. Save catalog. Where is it? Save catalog. There's DB. It's the same database handle, but we're calling the save catalog method, which was retrieved by, where do we, oh, this was up here, this web service call from get events, MsPASS get events thing. And we save it with save catalog. Similarly, we did the same thing with, we do the inventory. We use MsPASS get stations method right here to retrieve all the stations we need for this data. And we call this thing called save inventory. That's a C of CRUD. We're creating entries in a database that are making things in this case, is writing into site and channel. We'll get back to this one later, but the processing is, first order processing is done here. Save data. So I'll just talk about what this is doing. This is the same kind of thing I talk about. I don't know where this is coming from. How do I get rid of this? I gotta close that. This is that same kind of thing. So a cursor find over mini-seed. We're going to loop over mini-seed data. And that the loop will say doc in cursor, just like I saw other examples. Read data and apply an algorithm called dtrend, which is actually a wrapper around an MsPASS function. So is filter. And then we do two custom functions to set the P and S arrival times and do a windowing around the P wave arrival time. This thing cleans out a bunch of debris, the janitor. That's another long story. And then we save the data. So this is what populates WF time series. Now, I went to all that because this thing is important, right? There's several things important in this about saving data. Storage mode equals file tells it it's going to write data files. And you can specify a directory, and there's quite a complex recipe. I'm not going to go through the whole thing. But what this is going to do is create files. The way this was written, it's going to write, essentially, we'll see it right here. If you look here, that these files are the same names as the mini-seed version. But they got written in a new directory. So that's the way the writer works with files. Somebody asked about files don't overwrite either, but the best way to do it is, easy way to do it is you just put a new directory if you do intermediate result. But the other thing that's important is to add this argument for a data tag, because that will add an entry for every document it saves that has a unique tag that you know that this was this state, this save state. So I can retrieve everything only in those with that tag. We'll see. Probably, I don't know if we'll have an example of that or not here. So to show you how this finishes, this little block, I'm not going to dwell on it. It's a similar loop to the one I showed you about ensembles. It's going to loop over source IDs. It's going to basically mostly what it runs is it reads data. It runs this function, which is used to bundle up an ensemble of all the things from a given event and organizes them, bundles them up into sizeogram objects, and then it saves it. So that's what this workflow did that you ran. And anyway, the reason I point that out is when you go back and read this later, and I'm going to get moving here because before I go over on some things, so there aren't that many minutes left. So, so we saw examples of this, right? I was looking through this is just iterating the same thing. So there's reading data. We've seen many examples of that. I guess I didn't run this blocks yet, did I? Yeah, we did that one. So reading, we saw examples. This is a time series. This is kind of reiterating things I did earlier. And yeah, well, let's move on. So you go back and read some of this stuff later. I want to make sure I talk about this because I'm running out of time here, I realize. Again, I think the details of this are better digested independently. So you can look at this, follow this link to last year's course, which has some more extensive examples. I'm going to just show you a few of them right now. And the right page in the user manual, because that kind of minutia will not stick. But I want to just tell you, I'll breeze through it right now, which is the simplest kind of query. What this is the MongoDB query language, is subsources call MQL. Here's a simple example, which is all I'm going to do is say a match station name. So you give it a dictionary what's the key that it should match and what's the value that it should match. So this says find for me all data from station 034A. And the answer is there is only one. And in the site collection. There weren't multiple epochs of this station. Station data often have time periods where something changed, but site often does not, because it's usually the station doesn't usually move. So if you do this with channel, you'll get multiple records. But anyway, that's the point. Is this is an equality match. So it just says key and the distinct string that's supposed to match, or the distinct value that's supposed to match if it's an exact match. More commonly, you have something like this, which is a range query. And that syntax gets a little weird. This is a time range query, or this is latitude, this is data in a box. So the way, it's a little weird if you haven't worked with inline Python dictionaries before, which is this with the curly brackets syntax. That's going to be real confusing. But this says that this is a dictionary. And the way it has to be done to give this query is that what key is to be tested is the key for that dictionary entry. Actually, it might be helpful. Let me do this. Let me just show you what you could type query lat. Okay, so that's kind of a confusing syntax, but see how that does? Because that is kind of weird. You see, it means that value associated with it is this. So that's the syntax MongoDB uses for arithmetic operators like greater than or less than or equal to. It has to have a $sign, and it has some magic names like $GTE, $LTE. You can find it in the documentation. Say these are the things you'll not absorb, but it says find me stations that are greater than 30 degrees, or equal to 30 degrees, and less than or equal to 35. And the other part of the query that is for the longitude between greater than minus 110 and less than 100. So if you look at this table, that's what this thing does, and that's what it returns. It's actually 76 stations in that particular database. So it doesn't need to print them all, but you see that they all satisfy that rule. So that's a similar query is used for time range queries. That you say start time, for example, between a time range, for example, would be used that way. The other one that's important is this one uses what's called a projection, which means you don't always want to print everything that's out in every document. Oh, I also did something a little tricky here, which I didn't show you. If if you've never used pandas or a data frame, as they're called, they're actually really useful for tabular data. And this works as tabular data. So in this case, I converted the data to a pandas data frame to make it easier to read and print. That's all the trick I did here. But it isn't really naturally a table. I converted it to make it look like one. And this data is natural that way. Some data, not so much, because it may not be, every attribute may not be matched. In this case, it is, though. And, so a projection is a way to limit what comes out. You could reduce, it are also, so that's what's in this, but you could also sort the output. And so this is quite a complicated example, and I'm going to stop here, I think, because, well, no, I'm not going to stop here. Read this at your leisure. Use a Unix regular expression to find everything that's in all the things that stations that start with Z. So you got station names Z, and it only prints start time, end time from, and it's querying, in this case, channel. It's an example for two things, showing how to sort and how to reduce, not return everything in the documents. You're only going to return what's listed as keys here. This one's important to make things go faster sometimes. And it's important to realize that MongoDB's magic is that you could put anything in there, but anything you're going to query against a lot, you need to build an index for it, because it will go really, really slow if you get a big database and you don't have an index on it. Because, for example, if you have 10 million records in a database, if you don't have an index on stay and you wanted to select by stay, it has to go through the entire database to find it. However, if you index it on stay, it happens like that, because the index gives cross-references to it can pump, it can find its way through the database and doesn't have to read them all. So this just illustrates to you how to do that. This is this is actually, I guess that's the difference in this is how you make one. And this should be slightly faster. What's the differences? Not very different, because it's a small collection. If you have a big collection, that would make a huge difference. Okay. Another example. So I'll be doing. I'm already over time. I got to move on here. Let me think. You can look at this. We did a lot of stuff like this already. You can read through this about, these are just more examples. And I think they're best done by just working through it, reading the examples instead of me blabbing at you anyway. We talked about this a little bit before, but here it is in one place about what the standard collections names that we use in MsPASS are and what their purpose is. This is what I wanted to get into, this part here about kills. Anything that's killed puts an entry in the error log, in this elog collection, and you could pull out the message like this. There's a whole lot of stuff in there, and so that's important. It's an important component of sorting out data problems, is pawing through the elog collection. The other part of killed data is this thing I mentioned before called the cemetery. Whenever a data is killed, it will leave a record in cemetery. That includes the error message, what killed it. So in this case, it says it was killed because there was a window mismatch. I was asking for data which didn't exist. it also has this strange name of an abortion. An abortion is a datum that was never born. Is caused in most cases like this one from a mini-seed error in the file. It couldn't successfully read the file, and so it created an entry, and it stored it instead of in the cemetery. It puts it in a different place because you have to treat abortions are a different thing to handle than somebody killed during a workflow. It means you have an input data problem. It's kind of a detail, but it's a new feature added only like in the last year. I'm sorry I'm over, but I really had to get to this one because read this over in detail, but normalization is what in relational database theory is called a join. And it's important for maintaining and managing your data because things like the source and receiver metadata are tiny, tiny things compared against a full data set. So for example, if I were to take a year of this TA data here, there are about 500 channel records. I would get about, if I had a year's worth of teleseismic data, of sort of modest, all teleseismic events from the TA, it's around 10 million or 20 million records. 20 million mini-seed records. If I had to have 500, those 500 would be duplicated by thousands of times if you put them in every one of those records in the WF database. So that's what normalization is used for, is to keep small things and be able to link them back to the waveform. And it's been around forever. And anyone using databases for managing seismic data, any relational database will have it too. But in MongoDB jargon, it's called a normalization, but it's really the same thing. But the way we do it in MsPASS is actually quite novel. In most cases, what we recommend is these things are cached. So see. This is just showing the data before and after normalization. What we do is we use this thing. Where do I define matcher? It's up here. I think it's a mini-seed matcher or something. I defined it up here. Can't remember where it is. I got to stop here. What this thing here, when it's created, this thing actually contains all the data for the channel collection. And when you read it, when you use it this way, on the fly as the reader goes along, it matches against it. That would be really, really slow if you did it with the database. So instead, what we do is load them up into a memory. And as the reader goes along, it just has to fetch them out of memory. And it's made a huge difference in performance than trying to normalize against the database. I mean, it's orders of magnitude faster. So that's what this little box shows, compares what normalization does. It pulls in things like this. Channel LON, channel VANG. Normalization pulls in records off keys value pairs out of the channel collection and that forth. So I did that part at the end really fast. I'm sorry about that. Read through it, try to do this quiz, and I will be available for tomorrow. What is it? Eastern time, 9 o'clock in the morning and 8 o'clock in the evening, U.S. Eastern time zone, daylight time. So come see me if you want to talk about some of this or ask more about how some of all this works. I'm sorry I did this last part pretty fast. So any last minute questions we can do, or people can drop out as they wish? think we've already lost a lot of people because I went over. So. All right. Well, do I end this, Tammy, or?
I go ahead and end it. But give a couple minutes chance for people to type out questions or raise their hand if they want to.
Yep.
We'll unmute them.
Oh, there's still a lot of people there. I think I couldn't tell from my view about how many people are still around. So.
And
Maybe I hope I didn't blow you away. I'm sorry about that last part. I went way too fast there. But I didn't. But I really do think that you should be able to read through that. And if you can't have problems with it, come talk to me on one of these help sessions or the office hours tomorrow. Or send me or go on Slack. I'll be monitoring Slack this afternoon. And tomorrow.
Just a quick one, maybe the indexing was already done when we ran the pre-processing script, right?
That is correct.
For the database that we use. Okay.
Yep. It goes pretty fast. It actually uses. It's actually implemented with the actually same lib minic that Iris now Earthscope distributes. So it's written in C, and it's actually run with just a Python wrapper. So it's really fast.
Okay.
The timing is in that notebook, I think. I timed that. Is that there's a timing loop, but maybe I did. It's only a few seconds. We also did it in parallel in the notebook. We'll come back to that on Wednesday and Friday. It's a parallel. That's actually the one parallel construct in that whole workflow. Thanks everybody for their time, and come to the session. We'd love to talk to you. We can chat for a while longer. We don't have to be in this giant group. So, okay. So I will say sayonara for today and talk to y'all tomorrow or Wednesday. All right.
Okay. Thank you, Gary.
Thank you.